where we had, I'm going to rewrite it. I know we already did this one, but where we had x plus 1, x minus 1, or let's see, x equals negative 1 was a 0, and it had a multiplicity of 1 because its exponent, there was none, so there was a 1 right there. We had x equals positive 4, and it had a multiplicity of 2 because its exponent was 2. And then over here, we had x equals 0 because there's nothing with that x, so it could be written like this, x minus 0 to the third power, like that, or x plus 0, it doesn't matter because it's 0. And then that has a multiplicity of 3 for that one. So we had already talked about that problem. On B, we had to do a little more work because we had to finish factoring. For C, we got a lot more work to do because this is not factored into linear factors. For us to be able to do what we did on part A, we have to have everything factored into linear factors. So the first thing I notice right here in this first set of parentheses is everything has an x with it. What can I do whenever everything has an x? Not really cancel. We can like factor that x out, right? Which does like cancel one of the x's in what's left. So we could, it's called a greatest common factor, right? Where we're pulling something out of each one of these. So what we would have y equals, we could pull an x out of that first set of that first parentheses, and it's just going to reduce all the x's by 1. So we'll have x squared minus x minus 6. And we got x squared minus 7x plus 12. We're not going to mess with that one yet. So the x gets factored out front because in that first set of parentheses, everything has an x. Then I had told you guys over the weekend, if you can't remember how to do what we're getting ready to do, it would be a good thing to look over that. So it's not going to be a huge factor yet of things that you'll be asked to do, but it is going to come back up, especially when we get to rational equations. So you need to be able to factor x squared minus x minus 6. I need you guys to be able to do this quickly. I know that when Miss Martin teaches factoring, she teaches like the x method where she's got like the negative 6 on top and the negative 1 on bottom. And this is the number that you multiply by. This is the number that you add together to get. I don't love it. I don't love X method. I want you to be able to just like look at it and do it. You're doing it, but you're doing it in your head, right? So like you're thinking, I need numbers that multiply to get negative 6. So now I'll have x here, x here. Numbers that multiply to give me negative 6 are either negative 6 and 1 or negative 2 and 3, or I could switch my coordinates 6 and my signs 6 and negative 1 and 2 and negative 3. And then I'm looking for the option of those that adds together to give me negative 1. Which one is it? The 2 and the negative 3. So I would have a plus 2, a minus 3, or I could switch where those two are at. Doesn't matter for that. So that factors that part.
When do you like switch their sign to like positive when you go down?
Whenever you're like solving to get the zeros, that's when you'll change the sign.
So you just keep it the same way you have it on the X?
Right.
Okay.
You can draw the X if it helps you. You do need to be able to do this pretty well. So if this is something like you're a little shaky on, it might be a good thing to go back and maybe watch some YouTube videos on or look at. You got over here, you got just a plain x squared, so you'll have an x and an x. This time you need to multiply to get 12, but you'll add or subtract to get negative 7. To get that negative here, but a positive here. I know both of these are going to have to be negative. And 3 times 4. Negative 3 times negative 4 gives me positive 12. Negative 3 plus negative 4 gives me negative 7. So that's going to be a negative 3 and a negative 4. Now
Does it matter which way? Like
you could have x minus 4 times x minus 3 would be fine there as well. Now in this case, I would combine a little bit before I figure out what my zeros are, because I've got an x minus 3 and another x minus 3 here. So I would write it this way: x times x plus 2 times x minus 3 squared times x minus 4. And so once you get it to this part, you can do like we did on A and just find the zeros that go with this. So where I've got x alone, that's going to be x equals 0. I'm only going to write multiplicity if it's anything besides 1, because I'm afraid to rewrite it too many times. So that has a multiplicity of 1. I will get x equals negative 2. I will get x equals 3. That one will have a multiplicity of 2. And then I'll get x equals 4. Okay, so those would be our zeros for that problem. Our real zeros for that problem. These only have real, I guess. Okay, questions? All right, moving on to complex roots. Some polynomials will have roots that contain an imaginary number. This means that you will not see them on the graph. A good example is given over here of x squared plus 1. So x squared plus 1 is just your parabola, and it's been moved up 1. And since it's been moved up 1, it does not cross the x-axis. It does not have any real zeros. So if I wanted to find the zeros of this, whenever I have an x-intercept, my y-coordinate is 0, right? So the f of x right here acts like a y, and they've walked through it, but I'm going to do it step by step so you can see, because they didn't show a lot of work there. So that f of x, I could plug in 0 for that, and that would give me x squared plus 1. And then I would need to find x squared, so I would subtract 1 from both sides. So I got negative 1 equals x squared. And I would square root both sides. But when I square root both sides, I have a problem, because what do I have underneath my square root? A negative. And for real numbers, we cannot have a negative under a square root, right? So like when you were in Math 1, we'd just say there's no solution, just stop, right? We would tell you to quit. But in Math 3, what did you guys learn the square root of negative 1 is? It is I. Okay, so I is just a symbol that we use to help us deal with square root of negative 1, right? And this would equal our x. Technically, we need to put a plus or minus here, because when you square root both sides of a function, your answer could be the positive of that value or the negative. So in this case, my zeros would be, are x equals positive I and x equals negative I. I've got those two zeros there.
Does that work for every number or just negative 1?
If we had something like the square root of 7, we would end up with like I times the square root of 7. So you could still do the same thing. Your answer would not necessarily be just the I. It would have something multiplied by it.
Okay.
Yeah. So we are not going to go into great detail at this point on finding complex zeros. We need to know how complex zeros behave, is what we're looking at. So if we go to the next page, this is your key understanding. All imaginary roots come in pairs. So you'll notice how we solved that last one. That last step was to take the square root. And when you take the square root of both sides, you have to put the plus or minus. And so that part of finding your complex zeros produces two different complex zeros. So complex zeros, or imaginary roots, always come in pairs. Technically, I used the wrong word there. complex roots can be imaginary or real. Because like we were looking at on that ACT problem, a complex number is going to be A plus B times I. So a complex number, in this case, B could be 0, right? So you could have like 3 plus 0 i's. That would be a real number. Or you could have 3 plus 4i. That would be an imaginary number because it includes the I. Those are both called complex. So complex means imaginary or real. It could be either one or both of them together. When we talk about imaginary, we're talking about the ones that do include I for that. So imaginary roots must come in pairs. If A plus BI is a root of f of x, then so is A minus BI. Okay, so whenever we are given a root, they do this a ton. They'll only give you one of the imaginary roots. Essentially, what happens is the I part changes its sign. The A part, the part without an I, does not change its sign. Okay, only the I part changes its sign. So if we look at, like, example A, it says determine the conjugate of the following complex numbers. These, I should have said up here, these are called conjugate pairs. So like A plus BI and A minus BI are called conjugate pairs. So if they give us 4i, that's like 0 plus 4i pretty much. The I part changes its sign. So the conjugate that goes with it would be negative 4i. For B, if they gave us negative I, the I part changes its sign, so that'd be positive I. C and D are both complex numbers that have a real part and an imaginary part. So only the imaginary part changes its sign. So the 2 would stay as it is. But the 3i changes its sign. So we'd have 2 plus 3i there. And for D, we would have negative 4 minus 2i. Occasionally you might be actually asked to find these. Most of the time you just need to know they exist. If they tell you that x equals I is an answer to one of the zeros, then you have to know that x equals negative I is also 1 for that. Questions so far? All right. The fundamental theorem of algebra, as you can imagine, is a very important theorem that we need to know well. It's actually very, very simple. And the fundamental theorem of algebra just tells you a polynomial of degree n has exactly n complex zeros when counting multiplicities. So, for example, if I go back to this problem that we did over here, where we did part C, I had 5 zeros here, right? Because I had 1, 2, 3, 4, 5, right? I'd count that x equals 3 twice. So there were 5 complex zeros when I consider multiplicity, even though there were only 4 what we would call distinct complex zeros, because there are only 4 that are different from each other, but this one counts twice, so there's 5 total. So your degree always has to match your number of complex zeros. And keep in mind, again, that complex, it can be real or imaginary. A lot of times times when I see that word complex, I immediately go to imaginary because we don't usually call like x equals 2 a complex number. We call it a real number, but technically it is a complex number. So here is a type of question that they love to give. Okay, they give you this graph. They say the graph of the polynomial function f is shown in the figure above. It is known that x equals I square root of 3 is a 0 of f. If f has degree n, what is the least possible value of n? And so they've given us a graph. They have also told us it is known that x equals I root 3 is a 0 of f. And we have to tell what the lowest possible n value here, and n here is that degree, right? So we need to combine what we're seeing on the graph with the information that they gave us about the complex zeros. So I know for my zeros that x equals I square root of 3 is a 0 because they told me that, right? Can I see that on the graph? I cannot. Now I can kind of know it might be there because the graph takes this little bit of a like weird turn right here, like between here and here. It's just not like really perfectly smooth like we would expect. So that could make you suspicious that it's there, but you won't ever find it from the graph. So x equals I square root of 3, I cannot see on the graph. There is another complex 0. What would it be? Negative I square root of 3. There. So it would be negative I square root of 3 because even though they didn't say it, if you have one complex 0, you have to have the conjugate of that complex 0. So we got two complex zeros, and they didn't tell us that the multiplicity was any different than 1. So we are going to assume that both of these have a multiplicity of 1 because it asks us for the least possible value of n. Right? So maybe it's higher than 1, but we want the least possible, so we're going to say it's 1 for that.
And that's, you can't have like 0, something like that.
You can't have a multiplicity of 0. No. Then it wouldn't be a 0. If we add this to what we see on the graph, I've got two other x-intercepts. So real zeros I can see from the graph. So I know I've got x equals negative 1 and x equals 3. And I need to think about the multiplicities for these as well. So for odd multiplicity, remember that the graph crosses x-axis. For even multiplicity, our graph is going to be tangent to the x-axis, or it bounces off the x-axis. Okay, so at x equals negative 1, Kendall, do I have even or odd multiplicity there? It's even. And because they ask us for the least possible value of n, we will go with the lowest even number that we can use, which would be 2. So I'm going to say that has a multiplicity of 2. I don't know for sure it's 2, but I know they said least possible. So I'm going to pick the lowest number I can.
So if it didn't say least possible, could you choose like 4?
It could be 4, it could be 6, it could be 8. It would be a question that you couldn't really answer. There would be options you could have, but you wouldn't be able to answer it for sure if it didn't say least possible. And then, let's see, Michaela, for x equals 3, is that going to be even or odd multiplicity there? Odd. And what's our lowest odd that we can use? Multiplicity of 1. And so this covers all of our possible zeros that we would have. I've got 1, 2, 3, and this counts as 4 and 5 because it has a multiplicity of 2. So n would have to equal 5 for this problem. Okay, questions? You've got 4 zeros, but this one right here has to have a multiplicity of at least 2. So it counts twice. So you got 1, 2, 3, 4, and 5 are both right here. So that gives you your number of zeros. And your number of zeros has to match your degree. So that would be it. Okay? Questions? All right, moving on. Okay. Polynomial inequalities. This, I believe, is something you have not done in Math 3, although technically you are supposed to do like rational inequalities, which are similar in Math 3, I think, but you may or may not have seen it the way that I usually do these problems. So when we write f of x, we are referring to the y value on the graph of f of x. So if I see the phrase f of x is greater than or is greater than 0, that means the graph of f of x is above the x-axis. Another phrase they may use instead of f of x is greater than 0 is f of x is positive, because being positive would mean that you are greater than 0. And so if we flip that sign and make it a less than sign, then that means that the graph of f of x is below the x-axis. And this, of course, could also be written as f of x is negative. Okay, so some questions that they may ask you, it might say something like, where does f of x equal 0? So f of x equals 0 where your y equals 0. That's this whole x-axis, right? Everywhere you touch the x-axis. So they might ask this way. When they say, where does f of x equal 0, they're really asking for the x-intercepts, right? It's a different way that they might ask for the x-intercepts. One thing you'll see in this class is that they will ask problems in lots of different ways, which makes you a better mathematician because you're not just memorizing that, like these few things short term. You know what they mean and you can answer questions even if they're worded differently. That'll also be helpful for you going into college, where who knows what professor you're going to have, where they're going to be from, how they are going to word things, and you'll be more flexible with that. So this is really just asking for where the zeros are at. You would have x equals negative 3, x equals negative 1, and x equals positive 3. I'm going to erase my highlighting here so that I can answer the next part. If they ask us where is f of x greater than 0, it's talking about where the y coordinates are positive, which we said means that our graph is above the x-axis. So this f of x greater than 0 would be talking about this part of the graph and this part of the graph. And when they ask you a question like this, they want to know the domain where that happens, so your x coordinates. And so here is a place where the brackets versus parentheses matter. Okay, they ask us for where f of x is greater than 0. Okay, at negative 3, the function equals 0. We don't want to include that, right? So we could write it this way: negative 3 to negative 1, and we would have to use parentheses for that because we have a greater than sign, not a greater than or equal to. And then we would also have from 3 to infinity. The way that we would write this with inequality notation is we would do -3 less than x less than -1. X is greater than 3.
We should not need to include the infinity there.
Whenever you're on the end, so when there's an infinity, if I just say x is greater than 3, that goes up forever. So you don't ever want to write like this, 3 less than x less than infinity. Like technically, I guess that is correct, but you're never going to see an answer choice that looks like that. So just think about like on your x-axis, you're going from 3 over here, and that's all the numbers bigger than 3. Okay, notice I did not use any or equal signs there or any brackets because my function wasn't asking about where it equals 0. But for C, they asked me for where f of x is less than or equal to 0. So this time, x can equal 0, and I would need to use the brackets for this. So less than or equal to 0 is the places where my graph is below the x-axis. And for that, I would have, now I said use brackets, but can I use a bracket with a negative infinity? I cannot. You can never actually get to positive or negative infinity. So don't ever use a bracket with an infinity. That will be a parentheses. We'll do negative infinity up to -3. You will use a bracket here. And then you would have from -1 to 3. Or if it's inequality notation, this part, again, you don't want to do negative infinity less than or equal to x less than or equal to -3. You don't want to do an inequality that involves infinity. These are the numbers here that are just less than or equal to -3. So we'd say x is less than or equal to -3 and -1 less than or equal to x less than or equal to 3. Okay, questions there? Okay, so let's look at solving some inequalities. The first thing that you are going to do when you are solving inequalities, and these will be by hand, you won't be able to use Desmos on this. I don't mind if you do it to like check while you're doing your work, but it'll be calculator inactive whenever you see it. So you would need to first find where f of x equals 0. That means find the zeros, right? So you could even say that there, find the zeros. Then you are going to create a sign chart with the solutions from step 1. You're going to test values in each interval to see if the values in the interval are positive or negative. And then interpret the sign chart to answer the given inequality from the problem. Be sure to write your answer in interval notation and think about your endpoints. There, I guess inequality notation would be okay too. Can't remember if I think I added that in there actually, but we'll use interval notation is what I like better for that. So if I was going to do example 4, the first thing I need to know is where this function equals 0, because the question is asking me where this stuff is greater than 0, right? So that's asking me where the graph is positive, right? So I want to know where is it positive. got to cross 0, right? Because if I have numbers that are negative, my bank account is in the negatives, and I want to go up to the positives, then I need to add money until I cross 0, right? So, zeros are going to be the places where you switch from positive to negative. You're not going to switch from positive to negative at any other point for polynomials because they're continuous everywhere, right? Now, if you had like some crazy piecewise function, it could jump from down here up here. But that's not what we're talking about in this unit. We're talking about polynomials. And they are continuous. So to go from negative to positive or positive to negative, you got to cross 0. So x equals 3, x equals negative 1, and x equals negative 4 would be your zeros for this function. And so what we're going to do is create a sign line for this. So you're going to make a number line, and you need to include these 3 numbers. Make sure you go least to greatest. So negative 4 would be over here. Negative 1 would be here, and 3 would be here. Now, you got a couple options for how you can do this. You can make you a full-blown chart, which is what I prefer, or you could just test points. Okay, so let me show you what that looks like for both. All right, so if I just want to test a point I'm going to test some point lower than negative 4. It could be anything lower than negative 4. It does not matter which number you pick. You could pick negative 5. You could also pick negative 10. You could pick negative 1 million. You could pick negative 2.74, or not 2, negative 4.743. Pick whatever seems easiest to you. Negative 5 seems like an easy number to use here. So if I am thinking about negative 5, right, then I'm thinking of plugging in negative 5 minus 3 times negative 5 plus 1 times negative 5 plus 4. And that would be negative 8 times negative 4 times negative 1. And that would give me positive 32. No, negative 32, right? Because negative times negative would give me 8 negative. So that's telling me whatever falls in this section is going to be negative, right? And so then I could go do that same thing with a number between negative 4 and negative 1, right? There. And then I could do the same thing with a number between negative 1 and 3, and then a number bigger than 3, right? I think the chart is faster. Okay, so here's what I do if I'm doing the chart. I think of each factor separately. So I'm going to take this factor right here, x minus 3, I'm going to put it on the chart. I'm going to take x plus 1, I'm going to put it on the chart. And I'm going to take, x plus 4. I'm going to put it on the chart. And then I'm going to make my last line right here my answer line. Why is it not turned to red like I want it to? Okay? And so I'm going to do this. And so rather than plugging in a number into each one and figuring out the answer, all I really care about is the sign of the number, right? Because like when I had negative 8 times negative 4 times negative 1, I only care about whether it's positive or negative. The only thing that really mattered was whether those numbers were positive or negative, right? Because they were all 3 negative, and negative times negative gives me a negative. So all I really need to know are the signs. So what I can do is I can pick a number like negative 5 here, and I'm going to plug it in. Negative 5 minus 3 is negative 8. That's a negative that goes there. Let me change my colors though. So that's a negative right there, right? And then I can go across and just think about that whole thing. between -4 and -1 might be -2 or -3. Either one is good there. -2 minus 3 still gives me a negative. A number between -1 and 3 to pick. A good one might be like 0 or 1. 0 minus 3, still negative there. And then a number bigger than 3, such as 4. 4 minus 3 would give me a positive. Now this is why this becomes quicker. Notice the number this switched at, right? It was all negative till I got here, and then it became positive, right? And that's what should happen. Whatever 0 goes with that factor should be where you switch from negative to positive. Or positive to negative if it's a little bit different. So that gives me this whole line, gives me the signs for that whole line. Then I can go down to the next line. Well, if I plug in -5, -5 plus 1 is -4. -2 plus 1 still negative. Notice right here, if I plug in 0, this switches to positive, and it's going to stay positive if I put in a bigger number. So that switch there, negative, negative, at -1, it switched to positive, right? And then for 4, if I plug in -5, -5 plus 4 is negative. If I plug in -2, -2 plus 4 is positive. And then any number bigger than that is still going to be positive. Notice that one switched at -4, right? So what this does for us is it gives us what we're going to have in each section. Negative times negative times negative gives us a negative, right? And that's what I did whenever I did this the other way. But here I'm going to have negative times positive. What's that going to give you? That'll be positive in that last line. Negative times positive. That one's going to be negative. And then the last one's all positive, so it's positive. If you have an odd number of negatives, you will get a negative. If you have an even number of negatives, you will get a positive in that answer line. So then, my problem is asking for where this is positive, so I would be looking right here and right here. Okay, that you're only looking at your answer line whenever you do that. Okay, so my answer for this would be, notice that I used a greater than sign here. So I don't want to use the brackets. I want to use a parentheses. I don't want to include those points. I would have -4 to -1 and 3 to infinity. That would be my answer for that one. Okay, questions? All right, let's try another one of those. Here I would get x equals -2 as my 0, and I would get x equals +5 as my 0. Now, x equals -2 does have a multiplicity of 2. I don't have to make note of that or put it on the number line twice, but I do need to make sure when I put my factor up here, x plus 2 squared, that I use that square. Don't leave the square off. So my chart here would look like this. I'd have -2 and 5. And then I would take my factors. X plus 2 squared would go here. Got to make sure you include that exponent because it's part of the equation. Then I'd have x minus 5 there. And then I would have a line for my answer. And I would just draw in my chart here for this. Now there's something kind of neat about this. X plus 2 squared. What happens to a number when you square it? It's positive, right? Every time. So this whole line right here is positive. You don't even have to think about plugging something into it because no matter what number you plug in, you're going to get a positive number or possibly 0, but we've already got the zeros covered, and so we don't need that, right? So positives all the way across for that one. For x minus 5, I'm just picking a number that falls in that region and plugging it in. So like something smaller than -2, like -3. If I plug in -3, -3 minus 5 would be -8. That's negative. If I pick a number between -2 and 5, maybe 0 or 1, 0 minus 5, still negative, right? But here at 5, we're going to switch, right? We kind of know that because it's a 0 that goes with us. If I put in a number bigger than 5, like 6, 6 minus 5 is positive there. And so to find your answer, if you have a positive times a negative, that will give you a negative. Here, if you have a positive times a negative, that will give you a negative. And here, you have a positive times a positive, that will give you a positive. So this is telling you the sign of your final problem. Now, for this problem, we need to know, is it positives or negatives that we're looking at? To do that, you're going to go back up to the original. And this question is asking us, where is it negative or 0? Because we do have a or equal to sign, right? So if we're looking for the negative parts, that would be here and here. But we do have an or equal to sign. It can also equal 0, right? So like you might be tempted to give the answer as this. It would be negative infinity to -2. You would use a bracket because it has a or equal to sign with the question. And then you would say from -2 to 5, like this. Technically, that is correct, I think. You're kind of counting that -2 twice. Answer choice would never look like this because you've got brackets at -2. So you're including -2, right? Which means there's no need to even talk about -2. You could just put that together and it would be negative infinity to 5. This is what you would see as the answer there. However, if I change this problem and make it a less than sign where I don't have the or equal to, then I would have parentheses everywhere. -2 would not be included, and I couldn't put it together, okay? So you have to pay close attention to whether you've got that less than or equal to or greater than or equal to, or just the less than or greater than for that.
So, like, if it was just negative, like, or, less than, what would it?
If it was just less than, the answer would look like this. Negative infinity to -2, parentheses, if just less than. And -2 to 5. So you'd have to list those two pieces separately because -2 could not be included if it was just a less than. The signs tell you a couple things. If it's less than or greater than tells you whether you're looking for positives or negatives. So if it is a greater than, you're looking for where the graph is. You're looking for the positives as being your answers. If it is less than, you're looking for the negatives being your answers. The or equal to part tells you whether you use parentheses or brackets in your answer. All right. Oh, gracious, we're running out of time. Okay. I'm going to do this really fast. We kind of talked about it a little bit already. They want to know the degree of the polynomial represented. First of all, you must check to make sure you're going up by the same number. This goes up by 2, by 2, by 2, by 2. You've already learned how to do this to some extent because I taught you how to tell if things are linear or quadratic, right? So this goes down 1. This goes up 2. This goes up 5. This goes up not linear. That would be first degree if it were linear. So then you would do your second difference, and so this goes up 3, up 3, up 3. So this is quadratic, and that would be a degree 2. So I mentioned to you that we can tell by doing, like, we would call that a second difference. We could do a third difference or a fourth difference or a fifth difference. So if we look at B, you just have to check to make sure that your x-coordinates are increasing by the same amount. If they are not, then you're going to have a hard time deciding what's going on. You have to look at slopes. They're probably not going to ask you that anyway. Then you are going to look at your y-coordinates. So this goes up 2, up 10, up 17, and up 23. Hold on.
Was it degree of 2?
Because the second difference was constant. So we did our differences one time, and they were not constant, but when we did them again, that was a constant number. Have I got this right? I think so too. Okay, maybe it's gonna work. All right, I guess it's gonna work. It's gonna work. Okay. All right, this goes up 8. This goes up 7. This goes up 6. Is this second degree? Is it quadratic? No, because we're not getting the same number. But if we do it one more time, this goes down 1 and down 1. Now we're getting a constant value, right? So this would be cubic, which is a type of polynomial, and it has a degree of 3. So however many differences you have to do, that until you get a constant, that's the degree of your polynomial.
Okay, so like we meant one. Okay, so it's just 3 differences, degree 3.
Right. Right. All right. Even and odd, we're just not gonna have time to do. We're gonna have to talk about that tomorrow. So let me